the invitation and for listening to me. So I want to tell you about my favorite subject, which is algebraic geometry, which is what I do. Something about how this subject came to be historically and what it's trying to do, and some applications. So the starting point is just this very simple picture that I hope you all recognize from high school, where we have these lines with various equations, points in the plane. We work on the real plane, and we torture students with this kind of picture. So this is like high school geometry. But this actually came a bit later. The earliest proper geometric consideration goes back to the Greeks, ancient Greeks. So about 400 years before the Common Era, Greek mathematicians studied conic sections. So the idea was that they studied three-dimensional geometry, and in particular they discovered that if they take a rectangular cone, which is this red double cone, and cut it with various shapes, then they get a lot of interesting geometric objects. Like they get the circle, but they also get, in the same construction, they get ellipses, they get parabola when they cut this cone with a special plane, and they also get two-sheeted hyperbole. So this is a really interesting discovery, because this put these different geometric shapes in a kind of same footing, that you can get all of them as sections of this rectangular cone. Much happened after that. So they didn't have coordinate systems, at least not in the modern sense. Coordinate systems came into mathematics sometime after Descartes. It's called the Cartesian system. It was really systematized by Descartes' students, so sometime in the middle of the 17th century. So now in modern mathematics, we would say that this rectangular cone, okay, this is half the cone, but it has some kind of coordinates, some kind of equation like this, that x squared plus y squared is z squared. So this is basically, we might say that this is a circle of radius z as z moves up. That traces out the cone. And then we intersect it with a plane, and that plane has a linear equation. So z is ax plus by plus c. And if you substitute z in, then you get, combining the two equations, we get this quadratic equation, which you tidy up a little bit. We get this standard quadratic equation of in the plane. So now we only have two coordinates. We eliminated the spatial coordinates, so we get this coordinate equation for a general conic, or general conic section. And then this is still something which is usually discussed in elementary geometry courses. You know, the classification of plane quadrics or two-dimensional geometric objects given by this equation, which has one of these equations. So this is still sort of senior high school material, that we get the circle, the ellipse, and then the parabola is a special case, and then hyperbola. Okay, so this is all very standard, and then we can draw pictures and visualize it in this way. But so we want to kind of move on, and the next step was taken by Newton very soon after the introduction of the Cartesian system. So Newton studied cubic curves. So he said, okay, quadric or conics are well understood. What happens if I think about cubics? So he would not have drawn exactly these pictures, and he would have not written these equations. These are modern equations for some cubics. So cubics, if you draw them, I'm now going to take this special form for a cubic called the Weierstrass form. So this is a 19th century rewriting of the kind of thing that Newton would have done. You get different kinds of cubics depending on the equation you take. So this actually came up in Dimka's talk yesterday. This is called the cuspidal cubic, and that was one of the examples in Professor Dimka's talk yesterday morning. Then there is this equation, or some equivalent form. This is called a nodal cubic. So this is a self-intersecting cubic which has a singular point here. This cuspidal cubic also has a singular point here. And then these are what are called non-singular cubics. So there are no singular points. And at least the real pictures could look like this. It could have one component, or it could also have two components like that. Sorry. So this is what algebraic geometry then really is. So one thing we could do is we could take a polynomial in some variables x, y, and then try and solve that polynomial in the plane. So in other words, try and find the solutions to the equation f(x, y) = 0. And so, for example, you can think of x and y as real numbers. So this is what we do when we start drawing this picture, that we say there's the y coordinate and then the x coordinate, and then we really think of x and y as real numbers. But then a big discovery was, it's not such a difficult thing to say, but it really has led to revolution of the subject, that you could replace that. So you could say, okay, I don't want real numbers, but maybe I want complex numbers. Now, complex numbers is, we are doing polynomials, so we can evaluate polynomials in complex numbers. Of course, it's much harder to draw a picture with two complex variables, because to visualize that, you would really need 4 dimensions. But it turns out to be very, very useful as a generalization, in particular, of course, because the complex numbers have this property that it's an algebraically closed field. So polynomials in one variable always have a solution. So that somehow simplifies things. But we could also take rational numbers. So the famous example for this problem in rational numbers is, you will recognize this equation, a to the n plus b to the n equals c to the n. So this was Fermat's problem. So here, a, b, c are supposed to be natural numbers, and also n supposed to be at least 3 to make it interesting. And so this doesn't yet look like an algebraic curve, but I could divide by c. I could write the equation in equivalent way like this, or I could say this is x and this is y, and then suddenly I'm talking about an algebraic curve. So suddenly I'm talking about the solutions to x to the n plus y to the n minus 1 equals 0 inside pairs of rational numbers. So it's the same problem. We are talking about an algebraic curve. Now that's an algebraic curve we could plot in the real plane. I won't be able to plot it off the top of my head, I think. I haven't thought through. But for example, for n equals 3, you can plot it. You get a cubic curve. But then we are asking for rational solutions on that real curve. So you plot it somehow. And then it's maybe something like this. I don't remember. And then you say, OK, so these are all pairs of real points. But I actually want rational points. I want points with coordinates a over c, b over c. And are there such solutions? So there are two. So 1, 0 and 0, 1 are always going to be solutions. But these are the boring solutions, right? So if you substitute back in, this would just be the solution where b equals 0 and a equals c. OK, so that's a solution, but that's a boring solution to Fermat's problem. But then the more interesting solutions, which actually don't exist, would lie as rational points on this algebraic curve. So this was a very interesting discovery. And in fact, before Fermat's problem was fully solved, it was known that for every n, there are only finitely many solutions. And this is a consequence of a very deep result in algebraic geometry. This was Falting's theorem, which said that if an algebraic curve is sufficiently complicated, then it can only have a finite number of rational points on them. But then you could also talk about numbers modulo some prime p. That's these numbers also form a field, but ring would be enough. We can always check whether a polynomial is 0 in any ring. And so you could generalize to other fields and rings, and then you get this very, very general theory. The point being that a polynomial is just such a universal mathematical expression that as soon as we can add and we can multiply and we can substitute some values for variables, then we have polynomials. So over any ring, polynomials make sense, and this makes it a very, very general construction. But the point is that it's still very valuable to think of solutions of polynomials as geometric objects, even when maybe your solution set is not so obviously geometric, like over the real numbers, Nevertheless, it still makes sense to talk about these objects as having dimension, having singular points, having maybe something like a topology, and it's a very, very rich point of view. Sorry, what have I done? Yes. So, of course, we don't just have to talk about plane objects. We can increase the number of variables. We had that before. We had the z variable, which was a space variable, but we can add more variables. And then we increase the dimension of our objects. So we will talk about not curves, but higher dimensional objects. And we can have also more than one defining polynomial, which will increase the complexity of the object. So I might be talking about 2 equations in 3 variables, or more defining equations. And so algebraic geometry studies geometric objects even by polynomial equations. That's the subject. So that's the subject I'm talking about. And I should say that many of my remaining examples will be geometric, but just to connect to yesterday's talks, this is where algebra would pick up. Commutative algebra would say, okay, we treat these equations as elements of a polynomial ring. They define an ideal, and of course that's the connection to commutative algebra. So the ideals you saw yesterday in some of the talks, those were basically my defining equations. So I would say that, for example, for this very simple case of an algebraic curve, the equation f(xy) equals 0, that might define an algebraic curve, say, in the real plane. But there is a corresponding ideal, which is the ideal generated by the polynomial f(xy) as an ideal of the ring of polynomials in 2 variables over the real numbers. So this is the geometric object that you could study. This is the algebraic object. And there is a very close interplay between the algebra and the geometry. Okay, so the next few slides will just give you some interesting examples of algebraic varieties beyond, or these geometric objects called algebraic varieties, which go beyond curves, plane curves. So after curves, the next simplest objects are quadric surfaces. So a quadric surface is given by one equation in 3 variables. So here the Q is some general quadratic polynomial. But again, we have seen an example of this already. Now I'm going to give a more interesting example. So the example that we saw before was the quadric cone. That was such an object. So that was given by the equation x squared plus y squared minus z squared equals 0. Now I want to say x squared plus y squared minus z squared is 1. Or I could take this other equation, z equals x squared minus y squared. So in some sense, these are all equivalent, but the actual pictures you get are different. So here are the representations of these 2 quadric surfaces. So this is a one-sheeted hyperboloid, and then this is some kind of slightly different representation of, as I say, essentially the same kind of object, but somehow embedded in 3 space in a slightly different way. And so these are very interesting, very nice algebraic surfaces. So quadric surfaces would typically be studied in a first graduate course on algebraic geometry. And one famous theorem known about them is that they are covered by families of lines. So you can just about make out these blue and red lines. They are lines in 3 space, straight lines in 3 space. So you have this very interesting situation that you have some object which is obviously curved, but it's somehow traced out by, in fact, 2 families of lines. And this is true for any quadric surface, and you can always kind of visualize it. So it's kind of a bit hard to imagine, but you have this curved object which is nevertheless traced out by lines. So I would say that's a very, very beautiful geometric picture. Again, the proof of this would be pure algebra. So if I wanted to prove this, then I would have to do some kind of algebra, and it's not difficult, but it would sort of hide this kind of very beautiful geometric picture. And this is already pretty cool. So this is actually used in design and engineering. So you could do this. So you could take some rods and arrange them in a certain kind of way, and you get this. It's a pretty object, but it's also used in engineering. It's also used in cooling towers. So the point is, you could make an interesting geometric shape, but you can reinforce it with straight rods, straight iron bars. So if you actually want to build this, then you can make it very, very stable, because you don't actually have to curve your rods inside it. You trace out the boundary by these straight metal rods, and that makes it very, very strong. So this is some sort of quadratic surface. This is some sort of hyperboloid, and it is used in the design of these cooling towers. Okay, so now we've done quadratic curves and cubic curves. We've done quadratic surfaces, then we can go to cubic surfaces. So that's again a very, very famous story. So this could be one equation of a cubic surface. This is called the Fermat cubic because somehow the equation is very closely related to the equation we saw here. It's just one more variable. And so Cayley in the 19th century, or Cayley and Salmon, discovered a very beautiful fact. It is not covered by lines, so this is once again something that would be proved in a graduate algebraic geometry course, that this is not what's called uni-ruled. It cannot be covered by lines, but it contains exactly 27 lines. And you can visualize this very nicely. So this is something I stole from the internet. The internet is a good source for pictures like this. So again, this is an honest representation of a real cubic surface, where actually I think all the 27 lines you can make real, and you can sort of represent them like this. Now, I have not seen any actual engineering application of this, but I would say it's pretty cool. So this is, again, a very famous theorem, and this is a kind of frequent topic of master's thesis, to study the 27 lines, and they have very beautiful combinatorics. You can ask questions about them over a complex field, but you can also ask questions over different fields as interesting Galois action. There's interesting group theory behind the 27 lines and interesting combinatorics. So that's some very, very cool material, and there are different ways of understanding this theorem. This is not, in a way, a difficult theorem, but it is a very, very rich subject. Just 27 lines on a cubic surface is really cool. And once you're done with that, then you can talk about the 16 lines on a biquadratic surface, and you can make this more interesting. Okay, I wanted to tell you about another thing, which is very cool, which is going back to cubic curves, that they have some very interesting algebraic structure. So this was actually in some form, this goes back to the early 19th century. Abel's calculations of elliptic integrals, but it was formalized a little bit later, maybe the second half of the 19th century, into this very cool statement that the set of points of a cubic curve form a group. So this is a very surprising fact, and so the statement is that you draw a cubic curve over any field. This is true over any field whatsoever, but for example, you can take a real cubic like this equation, or this picture that I drew for you before, this one component cubic, and then there's a very, very simple operation which says the following. I take 2 points, P and Q. I take the line through P and Q. That's a very basic operation that we learn in high school, of course. And then we take the third intersection point with the cubic. So just we remind ourselves that this is a line. It's defined by degree 1 equation. The cubic has a degree 3 equation. I substitute one into the other. I get a one variable equation of degree 3, and that will have 3 solutions. So one solution is P, one solution is Q, and then the last solution is going to be this new point R. And then there is a little twist that I have to reflect that point in the real axis. And this is defined to be the sum of the 2 points in this group structure. So this is very cool. Well, I mean, it's something we can do. It's certainly an operation. It takes 2 points and produces a third one. And one thing that's obvious about this operation is that it's commutative, right? Because if I take P and Q, or if I take Q and P, the line is the same. So the R is the same, so the sum is the same. So this is some kind of operation which is obviously commutative. What is less obvious that it has an inverse. If you interpret it suitably, you have to bring in something called a point at infinity. And what is the least obvious is that this is an associative operation. So remember, associativity would require P plus Q plus R I have, so I don't know, S is P plus Q plus S. Now, I don't have a picture here, but some books bring you a picture. To check something like this in this kind of elementary geometric terms will be lots of lines. And there'll be lots of lines and lots of intersection points. and there is something quite non-trivial to prove. It is possible to prove it this way. There are other ways to see this group structure where associativity would be more obvious. But it is a non-trivial fact. It's a very non-trivial fact, and it's a very beautiful fact. And let me emphasize that it starts with this very, very simple idea that if I intersect a line with a cubic curve, I should have 3 solutions, and if I start with 2 solutions, I generate a new one. So this is the operation, and this operation produces this interesting abelian group structure. And the point is that it's given by relatively complicated polynomial equations. So if you can translate this very simple picture into polynomials, I'm saying we are doing polynomials, so I should be able to tell you, given the coordinates of 2 points, what is the output coordinates. And yes, it is a polynomial process, but it's somewhat complicated. So I didn't write down the equations because the equations are not that enlightening. Somehow the geometric picture is much more enlightening. And so this reinforces my point that we are doing algebra or algebraic geometry, but sometimes just brute force writing out the polynomials may not be the easiest solution. And so here is definitely the case that to actually work with this, you have to have some more sophisticated methods, either projective geometry or elliptic integrals or something else, because the brute force computation is quite complicated. And so I was told yesterday that this is a very old slide. So in the next lecture, you'll find out why this is a bad idea to do this. But I'm telling you that up until now, we have used elliptic curves for cryptography. The point being that information can be stored in the group structure of cubic curves using a variant of the discrete logarithm problem. And so as you'll learn in the next lecture, the discrete logarithm problem may be solved by quantum computers, so this may not be such a safe idea anymore. But until about last year, we didn't have a working quantum computer, so this was fine. Who knows what we have now? But this leads to what's called elliptic curve cryptography. And for that, one needs to find cubic curves with large complexity. And so I told you that some degree of complexity is the number of equations. Here we only have 1 equation. So the sort of thing you would have is that kind of elliptic curve. So that would be an example of an actual elliptic curve that would be used for crypto, probably even larger. But that gives you an idea of the kind of thing that might be used in elliptic curve crypto. So once again, the point being, this is not something you calculate by hand. This is not something you do on a piece of paper. So of course, what you do instead is you use computer algebra and computer algorithms to actually calculate in the group structure of an elliptic curve given in this rather complicated form. But it is all polynomials, it is all doable. So the ideas came from geometry, the computations will use algebra, and because we are doing very simple algebraic operations, this is actually completely feasible, even with very large numbers. Okay, so I want to give you some other ideas of bigger spaces. So higher dimensional, more complex spaces are, for example, used in variants of superstring theories. So this is one idea of theoretical physics, unification theories, theoretical physics, somewhat related to Professor Nakajima's talk yesterday. And so, for example, if I just take the same kind of equation, but I add 1 more variable and increase the degree to 5, then this is what's called a Calabi-Yau threefold. So I've my own research has been sometimes on Calabi-Yau threefolds. And again, you can sort of vaguely visualize this. I mean, we are now talking about just really artistic pictures at this point, because we are talking about a 3-dimensional object in 4 complex variables. So this gives you some kind of image of its complexity. This is becoming a bit of an artistic exercise. Okay, so for the rest of the lecture, what I want to do is I want to give you sort of actual applications, modern applications of algebraic geometry. So some of this is 20th century. So robotics I'll explain, but I think this is not really used anymore in modern robotics. There was a time 20, 30 years ago when people really cared about algebraic geometry in robotics, but it still gives you an idea of what is possible using polynomials. This particular approach is, as I say, it's not really used anymore, except in like fun papers. But I think it still gives you an idea of the kind of application that's possible here. So what's a robot? So a robot is rigid moving parts connected by joints, right? That's a robot, something like this. Just the simplest possible idea. You might be a 2-dimensional robot, you fix a point here, you have some joint, joints are free to move, and then you have some fixed rods, and then you have this thing called the end effector, so some kind of robotic arm. And then, okay, so simplest possible system, two rods connected by a joint moving in the plane. And want equations for where this end effector will go. So you work out your sines and cosines in trigonometry, and then you call your sine and cosine C and S, and then you get some polynomial equations. So the point is, Euclidean distance is basically a polynomial thing. So basically I'm saying sine plus cosine, sine squared plus cosine squared is 1. That's a polynomial constraint. And then I can work out, using trigonometry, what are the coordinates, the px and the py of this end effector. So that's a very simple system, but it's already a constrained polynomial system. We get two quadratic constraints, and then we have this linear expression for our target. So once again, it's very simple ideas. We translated trigonometry into polynomials. Now this is boring, but there are more interesting, slightly more realistic models, and one is called the Stewart platform. So the Stewart platform it has moving rods also. It's a slightly more complicated thing, but it has more interesting motion. So this is another animation I stole from the internet. So 6 rods moving in a certain kind of complicated way. So this is beginning to look like an actual robot that you might care about for your coffee table or something. To pour, to spill other people's coffee, this might be quite useful. Okay, so the point is, once you put a little idealized triangle at the top, some kind of mug at the top, and you want to work out the movement of it, it is actually pretty complicated. So it has some kind of space of motions, and the geometry of this problem, here's a system of polynomial equations that describes its kinematics, describes its movement, and it is given by some kind of space curve of degree 40. So things are getting more complicated and things are getting more interesting, but you still get this curve, which is not a plane curve anymore, it's a space curve, and it has some nice polynomial equations. So once again, you can study this equation or this problem with the methods of commutative algebra and packages in commutative algebra. So the kind of thing that I think we'll hear about tomorrow, for example, singular. And then the ultimate goal might be to help in some kind of real-life application. So this is an actual robotic arm which actually builds a car. And so the aim would be to precisely describe the endpoint of the robotic arm. And there are all sorts of practical considerations, which means that maybe you want to refine this approach, or maybe in any case you want to use machine learning instead of computer algebra. But this is certainly something that people have cared about in the past. And a lot of the algorithms to study polynomial equations were actually developed as a response to requests by a group of experts in robotics. And some of the more interesting contemporary platforms or computer platforms like Bertini were still developed out of that group that initially started as a group in robotics. So more interesting and more contemporary idea is polynomial equations in systems biology. So I'm going to tell you about one very particular paper that I've read, but I don't understand the biology, of course. I have a schematic picture here about some tissue structure. So here you have some kind of cells forming some kind of tissue, and there is some question about what are the biological processes, and it leads you to a dynamical system. So these are different compounds in your soup, in your liquid, different chemical compounds that the cells are passing to each other, and you get this sort of complicated set of, well, these are differential equations in the first instance, so these are kinematic differential equations for the changes of different substrates in your structure. But in particular, the very least you want to understand is the equilibria for this system, and of course for the equilibria you get 0 on the left-hand side, and you get a sort of elementary but complicated set of coupled quadratic equations that you want to understand the positive real solutions, because we are doing chemistry. We are no longer really interested in complex numbers, we are interested in positive real solutions. So what this kind of approach wants is to find, for example, the positive real solutions of a set of polynomial equations describing your equilibrium. So once again, we are back to the algebraic geometry, except that we might as indeed also in the Fermat case, we might only be interested in this part of the picture, positive real solutions. And so this particular paper goes back to my friend Heather Harrington and Ben Sturmfeld and collaborators about 10 years ago. They found that there are exactly 9 stationary points in this particular model. The method was the algebra of Gödner braces implemented on a computer, on a symbolic algebra platform. And they had a biological interpretation. And this was the first model that explained multiple cellular decisions, how cells develop in different directions, so specialization. So, and they fitted this to experimental data. And so this is very much ongoing work. So Heather Harrington has a whole group at the Max Planck Institute in Dresden, Institute for Cell Biology, to study contemporary questions in systems biology using algebraic geometry and other methods. I mean, this would only be one of the methods, but it very much comes in.